Welcome to this network theory lab, and today we are going to verify another network theorem. So this theorem is your maximum power transfer theorem. So that we have to verify using the MultiSim software. So let's begin this discussion. So normally the maximum power transfer theorem is applicable for the practical sources. Okay. So here I have just considered the DC source. Okay. I have just taken this DC circuit. Okay. So basically if we consider any DC voltage source. Okay. So normally if we consider it to be an ideal voltage source, in that case, there will be no internal resistance offered by the this ideal voltage source. So that time this internal resistance you can consider to be equals to 0. But normally this is not the case when we are considering any practical voltage sources. Okay. So all the practical voltage sources will be having certain amount of internal resistance which should be considered to be connected in series with the voltage source. So here you can see this very simple circuit to understand this concept, that we are having this particular practical voltage source, and in series with this voltage source we are having this source resistance equals to Rs, right? And this source resistance Rs is nothing but the it reflects the internal resistance of your voltage source. So because of this internal source resistance, we have to find out if we connect any load across this particular battery. Okay, so this is our complete voltage source along with this internal source resistance. So if you connect any load RL across this particular source, then what should be the value of RL that will allow the maximum power transfer from this voltage source to this particular load. Okay, so this is what we have to calculate, right? So this is what we have to verify actually. So here you can see that if we have this particular source whose internal resistance is to be Rs, and let us say we have connected any load resistance RL, in that case this power delivered to this load we can easily calculate, and that value you can write it as PL equals to current through this resistance IL. So we have to square it, IL square multiplied with the resistance RL. So this way we can calculate the power delivered to the load will be given by this particular expression. And here we can calculate this value of IL. So this load current IL we can easily calculate. So that will be equals to the total voltage applied divided by the total resistance offered by the circuit. So though it is internal to this voltage source, but this resistance must be considered, okay, while calculating the current drawn from this particular voltage source. So this current will be IL equals to Vs upon Rs upon RL. Rs plus RL, right? So that we can do. So if you square it, you will be easily show that this expression will be equals to Vs square multiplied with RL divided by Rs plus RL whole square. So to get this value of RL, for what value of this RL should be chosen so that we can transfer the maximum power to this particular load that we are interested in, right? So to do that, we normally we have to differentiate this expression with respect to RL, okay? And then we have to equate this differentiation equals to 0. So we have to calculate this differentiation with respect to RL, and then we have to substitute this differentiation value equals to 0, and then we have to simplify this particular expression, right? So once you do that, you will be able to easily show that this RL value should be equals to the source resistance Rs. So once you are going to get this, if you apply any load value which is equals to the source resistance Rs, that time we will be able to deliver the maximum power to the load, okay? And that maximum power you can easily calculate after substituting RL equals to Rs into this particular expression. So that expression you can easily see this RL will be equals to Rs, and here again we have to substitute to be Rs, okay? So this will become 2Rs. So here it will become 4Rs square. So this Rs and Rs will be cancelled out. So this maximum power which is going to be delivered to the load is equals to Vs square upon 4Rs, okay? The same thing we can also calculate by calculating the Thevenin equivalent voltage and Thevenin equivalent resistance. So that I have already explained how to calculate the Thevenin equivalent voltage and current in my previous lecture. So we can just remove this load resistance, and then we have to look from this particular terminal, and that time we have to replace this voltage source with its internal resistance. So that resistance itself is Rs. Okay, so therefore this Rth will become Rs. Okay, and similarly this Vth, you can easily see that because there is no circuit for flowing of the current. So because it is open circuit at that time, you can see that open terminal voltage will be Vth, which is same as equals to Vs, right? So this way we can theoretically we know this is the expressions for your maximum power which is delivered to the load. Okay, so now let's go to the this MultiSim software, and we'll try to see how this can be verified. Okay, so first of all we have to make this simple circuit. Okay, so let us suppose that we are having a voltage source 12 volt. Okay, so I'm just considering a DC circuit, right? I have not considered any AC circuit, because in the AC circuit analysis will be something similar. Okay, but there we have to consider if we are having any like capacitive load or inductive load. Accordingly we have to solve that expressions. Okay, so here we have just connected a 12 volt DC power supply, and I have assumed that let us say that this particular practical voltage source is having its internal resistance which is equals to 100 ohm. So that I have connected deliberately into the circuit, right? So I have connected deliberately. So in a similar way, if you perform your experiment, okay, because normally this resistance, internal resistance of the voltage sources will be unknown. Okay, you won't be able to say that what is the exact value of internal resistance. So that time we can also connect one resistance in series of this voltage source, whatever voltage source you are using the power supply in your laboratory. You can connect 100 ohm resistance, and then you can connect one variable resistance part. Okay, so here I have connected a variable resistance as a load, right? So here I have just taken this variable resistance whose value will be varying from 0 to 200 ohms to conduct this experiment. Okay, and in series with it I have connected one multimeter, right? So this multimeter is right now measuring the current, DC current it will be measuring, right? So this way you have to first form your circuit, and then we have to start varying our this resistance value, right? So once we'll start this variation of the resistance, right, that time you will find that there is a variation in the current that we are going to observe. And based on that, we have to make a simple observation table. Here I have made it. You can see this observation table. So I have taken this RL value, and that RL value, this load value is actually, I have varied from 60 ohm to 140 ohms, right? With the step size of 20 ohms, so that we can control here in the MultiSim. In a similar fashion, you have to also control your resistance value in your laboratory. Okay, you have to measure what is the resistance value you are taking, right? And then you have to conduct your experiment. Here I have taken this current I, okay, which is flowing through the circuit, and here I have calculated the power delivered to this 100 ohm resistance, which is in series with the your source. So here you can see this is our source resistance Rs. Okay, so when current is passing through this 100 ohm resistance, there must be a certain power which is going to be delivered to the this particular source resistance itself. Okay, so that power is normally lost. Okay, this is not available to the load resistance, right? This is the limitation of your practical voltage source, right? So that power I have written over here, okay, and that is written as P100, means it is power delivered to the 100 ohm resistance, and this is your power delivered to the load resistance when the load is mentioned as per this particular column, right? So that we can calculate easily, because the power you can calculate as current I square multiplied with the resistance, right? So that I have done here, right? So here you can see if we choose this RL equals to 100 ohm, right? So I just I'll be just changing this value. Right now it is 50%. So let me make it if I make it 40%, so it will be 80 ohms. And if you make it 30%, it will be offering your 60 ohm resistance, right? So once we execute this circuit, you can measure this current. Okay, it is 75 milliamperes, right? So the same thing I have noted down here. It is 75 milliamperes, corresponding to your load resistance equals to 60 ohm. And then I have calculated based on this current, okay, what is the power delivered to this 100 ohm resistance, which is your source resistance or internal resistance, and this is our load resistance. Okay, so this is the power delivered to the load, which is 0.3375. So here you can write I square multiplied with the RL. Okay, this RL value is here right now, it is 60 ohms and the current is 75 milliamperes. And that way you can do this calculation. So here I have done this calculation and then you will be getting this value. Right. Similarly, you have to increase this value again. Okay, so I have to increase this value. So if you increase this value, then you see I have just taken 40%. So at that time, this resistance will become 80 ohms. And for this condition, you will be getting current equals to here you can get 67 milliamperes. Okay, so that you can note down from here. It is 66.667 milliamperes. That current I have noted down and I have done this calculation, right? Similarly, for 100 ohms, okay, if you further increase this resistance value, okay, if you make it 50%, you will be finding this current is now 60 milliamperes, right? So you can see that once we'll be increasing this load resistance, current passing through the circuit, obviously it is going to reduce, right? So it is reducing, okay, because the total resistance offered by the circuit will increase. So 75 milliamperes, 66.67 milliamperes, then 60 milliamperes, and so on. So if you go down to 120 RL or 140 140 ohms your load resistance, then you will be able to easily calculate this values. Okay, this is the power delivered to 100 ohm and RL, right? So here you can observe one thing, that this, if you see, once we are increasing this RL value, okay, so this the power delivered to this 100 ohm resistance, okay, it is decreasing. Okay, so it is decreasing. And now here it is 0.36 watt, and now it is 0.29746, and here it is 0.2. But if you observe this power delivered to the load, okay, here you can see this power delivered to the load is 0.3375 watt. Okay, and now it has increased to 0.3556. And now when this RL is equals to RS, okay, source resistance, 100 ohms, okay, that time this value is equals to 0.36 watt. Okay, and if you further increase this RL value to 120, then here you can again observe this power delivered to the load is less than 0.36. Okay, if you further increase it to 140 ohms, again it is reduced to 0.35. So here you can observe that for RL value, which is equals to RS, okay, 100 ohms, the maximum power is actually being delivered onto the load resistance, and that time the power delivered to the source resistance is also equals to 0.36, right? And it means that only 50% of the power in will be delivered to the load resistance. Okay, if we are considering any practical voltage source, provided that this RL, this load resistance, is equals to the source resistance. So only 50% of the power can be transferred to this particular load, right? And it is easily you can observe that even if you decrease the RL value or increase the RL value from RS equals to 100 ohm, that time in both the directions, this power delivered to the load resistance is actually decreasing. Okay, so this is how we can verify the maximum power transfer theorem in DC circuit. So hope you must have understood. So while conducting this experiment onto breadboard, you please measure this resistance accurately. Okay, then only you will be able to exactly, you first measure this resistance and then you also measure this resistance. So that time there may be a chances that if you connected 100 ohm resistance, then there may be a chances that this may not be exactly 100 ohm. Okay, it may be a little bit greater than 100 ohm. It should be around 110 ohms or 120 ohms, or so on. Okay, because normally in the practical voltage source we are not able to exactly measure what is the exactly its internal resistance value. So externally we are connecting 100 ohm resistance while conducting the experiment, but that can be easily seen by measuring this resistance. At what value of this particular resistance you are going to get the maximum power, that we have to measure. Okay, and that time we can write this RL equals to, if this is 100 ohm resistance that you have connected externally, then the total internal resistance you can consider to be RS plus 100 ohm. Okay, and that time this RS plus 100 ohm will be equals to RL. Okay, so this RS should be very small normally, but you can do this calculation accurately that way. Okay, so I hope you must have understood. So try to execute the circuit on MultiSim and also try onto the breadboard. So thank you for watching this video and stay connected with the channel for more updates. Thank you.